Good day and welcome to Big Bad Tech. I'm instructor Jim Pytel, and today's topic of discussion is the electrical properties of squirrel cage induction motors. Our objective is to examine the electrical properties of the squirrel cage induction motor, like current, real and reactive power, power factor and efficiency, at and at other than the rated conditions on the speed-torque curve. This lecture operates under the assumption the viewers watch the squirrel cage induction motors mechanical properties lecture, available at the Big Bad Tech channel. If you haven't watched this lecture or only dimly recall its contents, by all means, please take the time to watch it now. Additionally, it is presumed the viewer is skilled in the analysis of balanced three-phase AC systems as well as AC power calculations. As you are no doubt aware, the speed-torque curve and power curve for a Design B squirrel cage induction motor looks something like this. There are several identifiable points of interest on these curves: the unloaded condition, the rated condition, the breakdown torque or maximum torque condition, the peak mechanical power condition, and the locked rotor condition. Let us begin our tour with the rated condition. For the purposes of comparison, let us consider a 2 horsepower motor with a synchronous speed of 1800 RPM intended to operate using 208 volt line-to-line 60 Hz 3-phase AC. Let us begin our tour with the rated condition. Inspection of the motor nameplate demonstrates this motor's rated speed is 1725 RPM. Given a synchronous speed of 1800 RPM, this corresponds to roughly 4.2% slip. A unit conversion demonstrates 2 horsepower is equal to 1,492 watts. An algebraic manipulation of the mechanical power formula, solving for unknown torque, demonstrates the motor produces roughly 8.3 Newton meters of torque at the rated condition. Let's now examine electrical properties at the rated condition. Further inspection of the motor nameplate demonstrates the motor's rated current at 208 volts is 6.5 amps and has a power factor of 0.77 at the rated condition. Apparent power for a balanced three-phase AC system is the line-to-line voltage times line current times square root 3. Substituting in the given values in the motor nameplate demonstrates the motor experiences 2,341.7 volt amps, or roughly 2.3 kilovolt amperes of apparent power. Real power is apparent power times power factor. 0.77 times roughly 2.3 kilovolt amperes demonstrates the motor consumes 1,803.1 watts, or roughly 1.8 kilowatts of real power input to yield the 1,492 watts of usable mechanical power output. Efficiency is output over input. This corresponds to an efficiency of roughly 82.7%. Inspection of the motor nameplate does indeed confirm efficiency is close to the specified 82.5% at the rated condition. Not directly specified on this nameplate is the amount of reactive power consumed by this motor at the rated condition. Even so, we should be able to calculate it given the data we have before us. An algebraic manipulation of the apparent power formula, solving for reactive power, demonstrates the motor consumes 1,494.1 VARs, or roughly 1.5 kilovars of reactive power. This amount of reactive power is cyclically exchanged between the supply and the motor and goes towards the establishment of the rotating magnetic field central to the operation of induction motors. Given the inductive nature of this motor, we should expect current through each winding to lag the voltage across each winding by a relative 39.6 degrees, where 39.6 degrees is the inverse cosine of power factor of 0.77. It's important to realize that all the data specified in the previous motor nameplate is at the rated condition, i.e. a single point on the complete speed-torque curve. This is to suggest that the data in the motor nameplate is but a tiny, tiny picture of a much, much larger landscape. Our goal is to discuss the range of possibilities at and at other than the rated condition. Let's start with the basics. First, the rated condition is an important condition on the speed-torque curve because motors ordinarily operated around the rated condition. Why would you buy an expensive 4 horsepower motor if you could get by with a cheaper 2 horsepower motor? Why would you try to use a 1 horsepower motor to do a 2 horsepower job? Use a 2 horsepower motor. At and around the rated conditions, we'll get pretty predictable results. If we were to zoom in on the far right side of the speed torque and power curve, inside this narrow region, the motor operates as one might expect. Namely, unload the motor, it'll speed up, and load the motor up, it'll slow down. Sure, there's a roll-off and it's not exactly linear, but if you squint your eyes just right, it looks linear enough. At and at anything to the right of the rated condition, the motor can theoretically operate more or less continuously without ill effects unless it's specified as having intermittent duty cycle. In contrast, anything to the left of the rated condition would be an overload condition, where the motor can temporarily operate, however, not for any length of time. If it remained in a sustained overload condition, we might eventually see this motor damaged or destroyed. If we were to restrict ourselves to the far right side of the speed-torque curve, think about this simple division between underloaded and overloaded and try to predict how the following electrical properties might respond to these two states. current, power, of which there are two types, real and reactive, power factor, and efficiency. Let's start with the easiest electrical property to predict, current. Undoubtedly, an underloaded motor should draw less current, and an overloaded motor should draw more current. I will be so bold to predict that any underloaded condition to the right of the rated condition will result in the motor drawing less than the rated 6.5 amps, whereas an overload condition to the left of the rated condition will result in the motor drawing more than the rated 6.5 amps. It seems logical. My question to you is this: what happens at the no-load condition, the far right-hand side of the speed, torque, and power curve, i.e. an occasion when the motor is spinning respectively fast, yet producing no torque and 0 watts of mechanical power output? Will the motor draw no current? If it does draw current, where is that power being directed? Remember, there's still a rotating magnetic field. Additionally, what's the efficiency at the no-load condition? The answer to all these questions really sets up for an understanding of the electrical properties for the complete operational range. Most likely at the no-load condition, the motor will still draw current, albeit a much smaller magnitude than the rated current. This is sometimes specified as the NLA, or no-load amperes, on a motor nameplate. If the motor is drawing current, the motor is still consuming power, of which there are two dimensions, real and reactive. Think about what's going on at the no-load condition. The motor is spinning, i.e. there's still a rotating magnetic field, meaning it will still consume reactive power, but it's not doing anything useful, i.e. the small amount of real power it's consuming isn't going towards useful torque, but rather it's going towards losses like heat, friction, and/or noise. In summary, in comparison to the rated condition, at the no-load condition, the motor continues to consume reactive power, yet less real power. Proportionally more of apparent power is being directed towards reactive power and less towards real. This means power factor decreases. We might therefore expect current through each winding to increasingly lag the voltage across each winding. Additionally, think of efficiency at the no-load condition. The motor still consumes a small amount of real power, accounting for heat, friction, and noise losses. However, the motor isn't producing any usable torque or mechanical power. Efficiency at no-load conditions would be 0%. In summary, at no-load conditions, current would decrease, power factor would decrease, real power would decrease, reactive power might remain relatively constant, and efficiency would be 0%. Now, start at the no-load condition and think about how these same properties respond as one increasingly returns the motor to the rated condition. Current should increase, power factor should increase, real power should increase, reactive power should remain relatively constant, and given more input is being directed towards useful output, efficiency should increase. It makes sense. Let's now examine overload conditions on the left of the rated condition. Think about what's happening to the left of the rated condition. The motor is producing more and more usable mechanical power output, yet it's operating at a condition above which it's been designed for. It's really more of the same we observe transitioning from the no-load condition to the rated condition, with one minor exception. Current increases, power factor increases, real power increases, and reactive power remains relatively constant. Really, the only exception is efficiency. Given the motor is operating in excess of its design capacity, we might expect efficiency to decrease. In fact, besides the relatively linear nature of speed and torque and power at the rated conditions, it's largely for reasons of efficiency that motors are operated at or near the rated conditions. Notably, motors are more efficient when they're operated at or near the rated conditions. Operating a motor at the rated conditions is like dropping Pac-Man into a maze full of dots. That's what it's designed to do, and it's going to do it well. Now keep in mind these are quick generalizations only. Peak efficiency may not occur exactly at the rated conditions, but close enough. Another overgeneralization I've made is with respect to reactive power. In truth, reactive power isn't really constant for this narrow range, and you might expect the motor to consume slightly more reactive power at peak mechanical power output and less at no-load conditions. This being said, reactive power is relatively constant, where the term relative is in quotation marks. I think the easiest way to illustrate these idiosyncrasies regarding real and reactive power is to plot real and reactive power consumption not as a function of rotational speed, but rather mechanical power output. At no load conditions to the far left-hand side, the motor produces no mechanical power output. The motor, however, still consumes a small amount of real power, accounting for losses like heat, noise, and friction. The motor additionally consumes an amount of reactive power necessary to establish the rotating magnetic field. As we transition to the rated conditions, the motor produces the rated mechanical power output. in our previous example, 2 horsepower or 1,492 watts. To yield this usable power output, as we demonstrated, the motor consumes an increased amount of roughly 1.8 kilowatts of real power, where a majority of this real power is directed towards useful output, and about 300 watts is directed towards losses like heat, friction, or noise. The motor additionally consumes roughly 1.5 kilovars of reactive power necessary to establish the rotating magnetic field. Finally, as the motor transitions to peak power conditions, the motor produces peak mechanical power output. The motor consumes an increased amount of real power and only slightly more reactive power. In summary, as mechanical power output goes up, real power consumed by the motor understandably must also go up. Reactive power does go up, especially at the end. However, for the most part, it's relatively constant. Let's now examine efficiency. If we plotted efficiency on the same type of graph, we might expect 0% at the no-load condition and peak efficiency at the rated conditions. Efficiency most likely decreases near peak power conditions since the motor is operating above its design capacity. As long as we're drawing a bunch of graphs, what about power factor? Power factor is the portion of apparent power being directed towards real power. At the no-load condition, a majority of apparent power is being directed towards reactive power, and only a small amount is directed towards real power. This corresponds to a low power factor figure. At the rated condition, more of apparent power is being directed towards real power, and reactive power remains relatively constant. This corresponds to an increased power factor figure. Finally, at peak power conditions, a vast majority of apparent power is being directed towards real power, and reactive power only slightly increases. This again corresponds to an increased power factor figure. Keep in mind, we're making serious generalizations for the far right-hand side of the speed-torque curve only at this point. We'll examine complete range in a moment. What's nice about these generalizations is that they're generally true for most squirrel cage induction motors. If you're looking for specific data about a specific motor, remember to always consult the manufacturer's datasheet for that specific motor of interest. Now that we've got a general idea of what to expect, let's discuss the electrical theory behind these generalizations and discuss the behavioral electrical properties like current, power, power factor, and efficiency over the larger range of the speed, torque, and power curves. I really struggled with how to model squirrel cage induction motor windings for the purposes of this lecture series. The way I saw it, I had 3 options: easy, not so easy, and super hard. The easy method simply visualizes each winding as a variable impedance. This method kind of works, but it ignores some interesting and important electrical phenomenon. Any understanding using this model would be superficial at best. The more complicated, not so easy method visualizes each winding as a different impedance components in series with a variable voltage source in opposition to applied voltage. This method takes a little bit more effort, however it yields more usable results. The super hard method uses the Steinmetz or T-equivalent circuit, consisting of a series parallel combination of stator resistance, leakage reactance, reflected rotor resistance and rotor leakage reactance, slip and magnetizing reactance, using super confusing calculus that incorporates functions of flux density, torque, and other things that are best ignored. Ain't nobody got time for that. In the interest of balancing completeness with timeliness, we're opting for the not so easy method, where each winding is visualized as different impedance components in series with a variable voltage source in opposition to applied voltage. This does require a little bit more involved circuit analysis than the easy method, but it yields a reasonably complete picture in a reasonable amount of time. Do not for a moment think this is an officially sanctioned model accurate in every respect, nor does it represent reality in every detail in every sense. Windings are not composed of variable resistors, variable inductors, and variable voltage sources. They're just windings. These are just imagined elements accounting for various effects. The elements inside the model of choice include a small variable resistance, which is meant to represent the losses inherent in the motor's operation. This could be resistance losses, core losses, sound losses, windage losses, bearing losses, or anything else that doesn't go towards real usable actual output. Any power consumed by this component would be considered a loss. I'd like to say this component is small enough that you could ignore it, but it isn't and you can't. The second component is a variable resistor, which is meant to represent the real power consumed by the winding that goes towards useful mechanical power output. For the purposes of this lecture, we're going to kind of lump together the losses and output components into a single variable resistive component. The third component is a variable inductor, which represents the reactive power consumed by the winding during operation. This is that portion of apparent power that goes towards establishing the rotating magnetic field in the stator. Although this power doesn't go towards useful output, but is rather cyclically exchanged with the supply, it's an absolutely necessary component of motor operation. Without it, the motor would just sit there and do nothing, kind of like your lab partner. All these components are representative of a motor's operational state on the speed-torque curve. At certain points, the reactive power can be greater than the real portion, and at other points, vice versa. You'd think there'd be a simple formula to account for the magnitude of each component depending upon the motor's operational state, but there isn't. The real component slopes gently downwards as a function of rotational speed, slopes rapidly upwards as the motor approaches peak power, then nosedives as it approaches the no-load speed. The reactive component does something totally different. The reactive component starts sloping downwards as a function of rotational speed, then rapidly skyrockets as it approaches the no-load speed. In the interest of time, for the purpose of this and remaining related lectures, I'm just going to give you the component values and let you figure out the consequences by yourself using Ohm's law. You do know Ohm's law, don't you? The last property illustrated using the not-so-easy method is the variable voltage source in opposition to applied voltage. This is meant to account for counter-electromotive force, or CEMF, a self-generated oppositional voltage the motor windings experience while in operation. You'll recall in the Squirrel Cage Induction Motors Mechanical Properties lecture, available at the Big Bad Tech channel, I explained the operational principle of Squirrel Cage Induction motors using primitive graphics that I thankfully will not repeat here. As a summary of the process, you recall current flowing in the stator windings creates a rotating magnetic field which induces current on the rotor. Consequently, the induced current flowing in the rotor creates its own magnetic field on the rotor, which then interacts with the stator rotating magnetic field such that the rotor is twisted or dragged along with it. An additional interaction occurs that I only briefly alluded to in the aforementioned lectures. As does the stator's magnetic field interact with the rotor's magnetic field similarly interacts with the stator, kind of like the force you'd feel against your foot if you kicked a soccer ball. The ball feels the force of your foot, but your foot consequently feels the force of the ball. Once the rotor starts turning, if you want to think of it this way, the stationary windings on the stator will experience relative movement of a magnetic field, as would a generator. As a result, an oppositional or counter voltage would be generated with the opposite polarity of that initiated the action. The magnitude of counter-electromotive force is proportional to speed. The faster the motor spins, the more counter-electromotive force is produced. At rest, counter-electromotive force would be 0 volts. As the rotational speed increases, counter-electromotive force increases. For our purposes, we're going to consider this a linear phenomenon. This is the effect that largely explains inrush. More appropriately, it's the lack of this effect that explains inrush. A motor at rest is not producing counter-electromotive force, and upon closure of a full voltage starter, the winding would experience all voltage. We'll examine inrush calculations and inrush theory in greater detail in later lectures. An extremely effective way of explaining counter-electromotive force is using these two simple examples. Consider a 20 ohm resistive component in series with a 20 ohm reactive component in series with a variable voltage source meant to simulate counter-electromotive force that happens to have a value of 0 volts supplied by a fixed 120 volt source. The total impedance seen by the source is roughly 28.3 ohms at an angle of 45 degrees, which experiences the complete 120 volt differential. An application of Ohm's law demonstrates that the source supplies roughly 4.3 amps at an angle of negative 45 degrees. You'll note with 0 volts of counter-electromotive force, the winding experiences the full 120 volt differential and as a result draws a substantial amount of current. Now consider the same 20 ohm resistive component in series with the same 20 ohm reactive component in series with a variable voltage source that now happens to have a value of 70 volts supplied by a fixed 120 volt source. You will note the polarity markers on the fixed source and the variable counter-electromotive force component specify that this is a series oppositional relationship. Both the source and counter-electromotive force simultaneously peak. However, given their polarity markers are in opposition to one another, an application of Kirchhoff's voltage law demonstrates the series impedances experience a differential of 120 minus 70, or only 50 volts. An application of Ohm's law demonstrates the source supplies roughly 1.8 amps at an angle of negative 45 degrees. You'll note with increased counter-electromotive force, the same impedance experiences less of a differential and as a result draws less current. This again explains the vast disparity of current drawn at inrush versus at the rated and no-load conditions, i.e. opposite ends of the speed-torque curve. Even if the resistive and reactive components stayed the same at these two extremes, which they don't, a motor at locked rotor conditions, i.e. 0 RPMs, will experience more current because there is less counter-electromotive force. Whereas a motor at no-load conditions, i.e. extremely high RPMs, will experience less current because there is more counter-election motive force. Like I said, we'll examine inrush in greater details in later lectures. More to the point of this lecture is that every component inside this model changes at different points of the speed-torque curve. Given specified supply voltage magnitude, counter-election motive force magnitude, and impedance values, it should be well within your capacity to calculate current and power. Allow me to demonstrate.